Okay.
Hello, everyone, and welcome to this new MLIR open meeting. Today we have Dumitru, who's going to present about embedded reactive programming in MLIR. Dumitru, take it away.
Thanks a lot, Mehdi. So this is, I'm a researcher in INRIA in Paris, France. And this is joint work with Albert Cohen from Google. And much of the work has been done by my PhD student who defended 3 days ago, Hugo Pompugnac. How do I? Okay. So I guess this presentation is the first one we are working on with MLIR for 2.5 years now, and this is the first presentation we are doing here. And it took a lot of time to believe that our ideas are mature enough to present them here. But the counterparty of this is that this presentation is quite dense, and it's half technical and half ideological in a sense. So one question you could ask is, why talk about reactive and data flow programming in this around MLIR? This is a legitimate question. And the answer is because there are already quite a few elements of it in the front end, in the back end, and in the runtime. So I tried to mark with R for reactive, for elements of reactive, not fully reactive, with DF for the data flow, various elements of what we discovered in the MLIR ecosystem. And you can see that Keras and JAX are the data flow full-fledged. Then you have elements of reactive behavior in Keras-RL. You have them also in things like ML program and the former TF executor dialect. Then in the backend, you have separate things. You have interaction, so elements of reactivity between virtual machines and asynchronous components and the iReflow dialect. So it's not full-fledged reactive, but there are elements. And then you have things that only embedded implementers of machine learning C, and these are the C drivers that you have to write in order to run some iRE code in an embedded context, and often shims that you have to write in order to interface with automatically generated ML code. And the idea would be that so it's almost everywhere, not in the middle end. We couldn't find it. There are multiple, quite disparate and ad hoc approaches. So if you look at what happens in the front-end side, you have the data flow from Keras, but this is quite independent from the elements of reactiveness that you have in Keras-RL, and independent from what you have when encoding recursive recurrent neural networks and so on. So it's often unclear what the semantics of these elements are and how to put them together, because some come into Python level, others at MLIR level, other even directly in C, like for the driver. Also, this is in the front end, and if you look in the back end, well, if you look here, you will see that you already choose an encoding. You have solutions for interaction encoding, not specification of interaction and reactiveness. And our proposal is that we would like to unify the front-end practice around the general purpose data flow specification that should go all the way from the front-end Keras, JAX, and Keras-RL. It allows representing everything that you have there, and also is present in the first dialects high-level dialects of MLIR, and then allow in a way this reactive data flow specification to be transformed progressively through the middle end into the elements of the backend. And we propose a few primitives that would allow this transposition of front-end reactiveness into backend. Okay, I have to click. So I will start with a few examples to explain the base of our proposal. So let's start with stateful networks, such as recurrent neural networks, and let's look at a specification problem. So the intuition is here. If you take a paper, the paper introducing LSTM, the intuition is data flow. Clearly, you have the diagram that is replicated everywhere. Now, when you start to implement this and you take Keras and you look at the generated code, you realize that a time-space conversion has been done. And instead of something that is data flow and reactive that executes in a cycle-based fashion with successive iterations, you have a single function call that receives as input the whole history, the whole time history. And so you don't have, you have a single function call and no state between calls. So you have flattened everything, and there's no more stateful behavior at MLIR level. Now, and you also discover that your data flow behavior is not as simple as that, because you have options like, for instance, return sequences that will decide when output is produced. And if you dig a bit more, you will discover more options, such as return state, such as stateful. And you will discover even that some of the options, such as stateful, make reference to an overall streaming semantics. So on top of data flow, you have time-space conversion and removal of the state. And then on top of this, you have another streaming level, which is the one where you keep a state between batches. So you have a sequence of batches and stateful behavior. But of course, you don't see this at MLIR level, because this is Python level only. And of course, this is a semantic mess. It's even difficult to understand what's happening when you are new in the field. This happened to us 3 years ago. And we didn't yet discuss features that are a bit advanced, such as training or reinforcement learning. But our claim here is that general data flow specification would support on one side the specification of all these aspects of a specification, the core data flow, also the options and the batches and so on. And if you want to generate batch code or code that receives all the input at once, or code that is that is reactive for embedded implementation, you could do this in all cases from the same source code through specializations or compilations. For instance, by setting some parameters to fixed Boolean values or numerical values, and then propagating constants and doing some local time-space conversions and so on, which is a form of compilation. Now, besides this specification-related claim, we also say that this semantic mess is causing missing opportunities for efficient implementation. You have, in some cases, it is difficult to specify efficient algorithms, such as gating-based algorithms or multi-period, when you know that certain inputs have a dynamic that is slower than the other. There is little code generation modularity, and in the end, because few people understand that the big picture, you end up with a lot of ad hoc solutions that don't work well together. So it's difficult to optimize, to understand, and even to understand to debug. I will now change a bit from general systems to streaming systems and to streaming implementations, more precisely. And here I'm counting not only stateful networks such as RNNs, but also convolutional networks, which may require a state at implementation time only. So in these, the intuition in these cases is also the data flow. So you have this classical diagram with the one sample received at each cycle, a step function that will take a state and update it in place, possibly, and then produce one prediction at each cycle. And if you look at what frameworks do when you compile such specifications, for instance, for RNNs, you will see that they perform always this so-called time-space conversion by assuming that you execute this for a fixed duration of time, and then you will iterate this step function on a table of inputs for that amount of time. So you get a fixed size loop over a tabulated input. And this is what you get. This is what Keras will produce in output, and this is what existing compilers can take as input and compile. That, of course, unless using ad hoc extensions such as KWS streaming or converting to global variables. And well, if you do this, if you use the existing compilers, and you want to do a real streaming implementation, you have only two solutions. The first one is to add a sliding window over your inputs. And this is something typically done by embedded implementers. And in this case, that the problem is low efficiency, because you will treat, you'll process every input the whole time the sliding windows is on top of it. The other solution, which preserves efficiency, is to simply take the finite loop of this stated function and manually open it and produce again something akin to what's on the top image. And in this case, efficiency is recovered, but the prediction no longer corresponds to training for subtle properties related to the fact that the distance to the initialization is not fixed and so on. Well, there are problems. And what we propose, and of course, everything, both these solutions require manual transformations outside of Keras or PyTorch. Our proposal, in a nutshell, consists in two, actually, MLIR dialects. One is a high-level data flow synchronous dialect called LUS, which introduces general-purpose reactive specification inside MLIR. It does so by incorporating the 5 primitives of the Lustra synchronous language, which allow the specification of stateful schedule components, hierarchy, and gated execution or predication. And you can see an example of this on the right side. So here, instead of functions, you will have data flow nodes. And you can see here that you have a model node that will instantiate the LSTM node that is here on top. And this node is a mix of red operations coming from the TF dialect, and blue, the data flow operations describing essentially what I presented in the previous slides, data flow. I will explain all of this in the following slides. Ongoing work on this is the synthesis. So we will be able shortly to perform the synthesis of training code, automatic differentiation, at this level, and something that is more in the future, work on resource allocation using previous work on the Lucille language. So this is the Luce dialect. The second dialect, which is called Sync, is the set of low-level primitives that are needed to transfer this semantics to the backend, allowing efficient and reactive execution without performance loss with respect to non-reactive implementation. Just a few keywords. So what we know we can express with our dialects, and most notably the Luce dialect, stateful behaviors like RNNs, reinforcement learning, attention, transformers, whatnot. Predicated execution, like resetting a network, sparsely gated mixture of experts, or a subcase of this, which would be multi-period activation. Mixing the ML code with pre-processing and post-processing code for data, sliding windows, and so on. And it comes also with another view to undefinedness and correctness. I will try to explain a bit later. Our compilation flow will maintain statefulness throughout the compilation without the need to convert too early into stateless functions or global variables, which keeps some optimization potential. And there's the potential in the future of reusing existing resource allocation approaches from data flow languages. Technically, how do we extend MLIR? So we add two dialects. So you can see here the front ends with Keras, Jax, and so on. The existing dialects of MLIR, the targets, and then we added these two dialects, Luce and Sync. The first one is the high-level data flow, the dialect, only 6 operations, including yield, which introduces the data flow programming paradigm. It's a new programming paradigm. And then this is the Sync is the low-level reactive dialect, which you can see as akin to the existing dialects that touch the interaction between concurrent components like async or OMP, but introduces primitives needed to implement the data flow synchronous one, and which has the good property of composing with any control flow specified here. It's not a different paradigm, it just composes. There is actually little code we needed to write, only a few transformations. We need transformations only for things that don't exist in classical compilation, like clock analysis, which is the way to ensure that single assignment is respected in the presence of predication. A certain normalization, which allows us to move from here to here, lowering, the lowering passes, and that's it. Everything else, causality analysis, bufferization, optimizations, all the other lowering are reused from stock MLIR code with no changes to it. And with this, we explored only 2 targets, but this was not our main goal. One is generating modular code with modular execution over a single core with some coroutines. And the second is a more classical synchronous compilation pipeline with the backend on IRE, it's CPU or GPU. In both cases, we invested only a little bit in code generation and optimizations, but still with no performance loss. So now let's move to more technical stuff. I will show for examples what our contributions are and how they connect each other to build a compiler for reactive specifications. And I do it in 2 phases. The first one shows how we enrich static single assignment in MLIR version to a reactive version that allows that is basically a low-level reactive dialect. And the second one is how on top of this, we can build an embedding of Lustre into MLIR, which is the high level, the data flow, the dialect, and then some experimental results and a conclusion. So this, you all know, this is static single assignment. You have here a function in C. Well, it's a part of a function. Its representation in a bit simplified MLIR SSA. And the only point I would like to emphasize here is that there's a difference between the SSA principle, which consists of two hypotheses, single assignment and causality, and the SSA formalism, which MLIR uses. SSA formalism is one implementation of the SSA principle. We will see that there's another one, which is the reactive language we use as basis for our extension, Lustre. And this is a close, this semantic proximity, the fact that both implement the SSA principle will help us in connecting them. Well, SSA, you all know it, it's very good, but it has some limitations when you want to manipulate reactive specifications with a cyclic execution model. So first of all, you don't have cyclic IO at high abstraction level. You can represent it. So here, the piece of C code I considered is an infinite cycle with read, compute, and write. But you don't know, SSA does not know that this is an IO operation. It's just a function. You can give, and this means that you can represent encodings, but not the semantic information that this is an input. And you may want other encodings. You may want these operations to have certain properties, and it's difficult to define them. Second, SSA is about describing one function, not concurrently running and communicate functions that synchronize and communicate, nor an execution environment that provides the data from the outside. Third, there is no synchronization between the execution of the cycle of the function and the environment. So, for instance, it will be correct to it will be a correct SSA code transformation to unroll this loop and perform 2 reads before performing 2 writes. This is correct, but if you want to preserve the semantics of interaction, you should not be allowed to do this. So you need a form of synchronization between functions, reactive functions, and environment. And finally, you need a better support for undefinedness or absence for such reactive behaviors. For instance, if you have a non-blocking data reception operation and no data is available, you will have an undefined output. And you may want, and LLVM undef and LLVM poison may not be the solution for the semantics of that value. For instance, you may want to be an immediate undefined behavior upon any sort of use in computations or in decisions. So how do we extend SSA to take these into account? We did something that looks like a concurrent design pattern akin to collective operations, but one that ensures determinism and provides some concurrency. This pattern is based on the execution model and causality of synchronous languages, but other mechanisms are possible. You may have heard of Berg synchronous parallel or C11 subsets. The property our extension has is that it's a conservative extension of SSA, providing what we need. It's not something completely on side. Semantically, we will reuse all the properties of the SSA semantics, adding the concurrent reactive functions element and the environment to it. And there is also true concurrency between non-dependent operations inside a basic block. So what elements do we introduce to provide this? Okay, so each reactive function will have its execution divided into non-overlapping cycles. These are the definitions. And cycles are divided by an operation called tick. This operation may not commute with any other. Once a cycle starts, it completes without external interference. You cannot stop a function from moving from one tick to the next. This is an atomicity hypothesis. And also, one function may trigger a cycle in another function using the inst operation, which is a form of synchronous call, but which is not a full-fledged function call. It just it just makes the other function to make another advancement in its execution. It does not create a new state. It does not preempt it at the end. This is on the non-overlapping cycle side. On the I/O side, we introduce I/O channel types and then two operations called input and output. So this is not new, but it's just a way of providing high-level abstract constructs for communication. And then we have an operation that allows you to explicitly manipulate absence without directly making reference to, say, LLVM.undef. So we can give it a semantics separately. The extension is conservative. So we don't remove anything from SSA, we just add these operations. The formal semantics is not losing any existing rule. We just add the rules that manipulate the concurrent execution state and the new operations. And furthermore, this extension, this new dialect, because it's a dialect called sync, smoothly integrates with traditional SSA compilation. So, for instance, correct SSA contract transformations would not break the reactive semantics we define. Let's take an example to see how everything works. So here on the right, we have a reactive function. We identify this through the sync.func keyword that replaces func. This function implements the same behavior we had in the beginning. So it's a read, some computations, write. Now, inputs and outputs will be done through channels. So this is an input channel, and this is an output channel, and both transfer float 32 values. The execution of the function starts here. And then if you look well, it's a loop that goes this way with a condition in the middle, which may or may not execute basic block 2. So this behavior never ends, but it is divided into ticks, into cycles by this tick primitive. So when execution arrives first at tick, the execution of the cycle is completed and control is given to the runtime. And when some other function requires the runtime for this function to execute another cycle, then the control will resume from exactly the tick operation where it ended in the previous cycle. It's really a simple mechanism. Cyclic I/O is done with the input and output operations. They operate on the input and output channels, and well, besides the syntax, there is not much to talk about, except that they may have various implementations ranging from function calls to shared memory and so on. How does modularity work? So, as I told you, for each reactive implementation may have multiple reactive functions. And one function, such as myFun here, may instantiate another, like this function which has a state and which is called sum. And from time to time, depending on a condition, myFun may decide to trigger one cycle of sum by providing it an input that will be placed on the input argument. And at the end, then it will give it control. This one will execute for one cycle between two ticks, tick operations. And when this is completed, control is given back, and the output value is taken from the output O of sum. So it's quite a simple way of creating coroutines. Now, all these yellow primitives of the sync dialect will be lowered further to calls to API primitives. I will show an example later, but it's quite clear that like classical SSA, this is not a good level for high-level specification, not even for a high-level intermediate representation. This is really close to this is really close to the implementation. You know how you divided your application into components. You know how you want to do your communications and so on. You just need the primitives to implement them. So for specification, we need to go really all the way to data flow, because it's the natural level. And for this, we went all the way to Lustra with a data flow synchronous language introduced a bit earlier, but this is the most cited reference, Popol 887. And the good question at this point would be, why Lustra? There are other data flow languages and so on. And there are also data flow-like formalisms like SDF and so on. First of all, it has a simple yet expressive concurrent and deterministic semantics. It contains both recurrence, but also gating, which is very useful. It is close in certain points, in certain semantics, fundamental semantic points, to both Keras like the data flow. In fact, it can represent any Keras specification, and to SSA form, because it's an instance of the SSA principle. And you can see this in the fact that it's globally sequential, locally concurrent, like SSA. It allowed the natural modeling of all ML applications we work with. And there is extensive work on code generation for such specifications. In particular, concurrent implementations of multiple flavors, static memory allocation, resource allocation, and so on. And of course, we have experience with it. Let's see what Lustra looks like. So again, we have our small code fragment, the same as in the beginning, and this is how it's represented in Lustra. So you already know that it's cyclic because it's a Lustra node. Lustra nodes have a cyclic execution model. Also, you know that inputs and outputs are cyclic. At each cycle, you receive one samples from the inputs and produce values for the outputs. It's a data flow language, and it's a predicated data flow language. So in order to execute a function like f conditionally, you do not place an imperative if in front of it, like here. Instead, you do subsampling using the when operation by saying that xx takes the value of x only when ck is true. When ck is false, then xx is absent, and so f is not executed. So it's the same behavior as here, only in data flow form. You also have the equivalent of the phi operator of SSA under the form a deterministic multiplexer, but here it's called merge, and you have to specify the condition, whereas for phi it's implicit. It's where does it come from? It's also a synchronous language, and the variables are not persistent. Their lifetimes end at the end of the current cycle. And you have an explicit operator that allows you to pass one value from one cycle to the next. It's called followed by. This followed by allows the direct implementation of the memory in an LSTM, and you need two of them, for instance. And like in SSA, to make values persistent, you need to explicitly copying them using merge operators instead of phi operators. So similarities. Intuitively, both are instances of the SSA principle. So you only instantiate a value at a certain point in the program. Globally sequential, locally concurrent. Cycles are sequential, but here you have inside a cycle you have concurrency. FBI followed by operations are almost like loop carried the dependencies. Merge operators are almost like phi operations of SSA. And the Lustre node is almost like an SSA specification with a single basic block, or two of them, one for initialization. Differences. In SSA, you don't have cyclic I/O. Here you do. Each operation is assigned to one cycle. And this is a form of high-level scheduling you need to preserve, and it's important semantically. And you can have predicated operations in and concurrency in the same scope. This is similar to the predicated SSA of old. And this means that inside one cycle, certain variables are present, certain are absent, and you need to you need a way to ensure that undefined variables are never used in computations. And this is done through static analysis called clock analysis. This is how they are called. Also, this predication also works on followed by on memory. You can have memory that is not passed from one cycle to the next, but every 2 cycles, and so on. And the final difference, and maybe the most difficult to accommodate, is the fact that this is the data flow, and you can have cyclic dependency. So here, for instance, C depends on itself. And so the dominance criterion is a priori not respected. So how would you incorporate, how would you start to think on how to incorporate this syntax into MLIR and compile it? So the first element, maybe the most difficult one, is absence, and the fact that you don't have dominance. So absence is a central concept in data flow synchronous programming, and each variable in each cycle is either present or absent. Correctness, a program is correct if absent values are never used in computations, so that the SSA principle is satisfied. And how do we check correctness? Using this, using so-called clock calculi, which is different from dominance analysis. We associate to each variable a predicate, variable x, to a variable x, we associate clock x, which is a predicate saying that is true in cycles where x is present, false in other cycles. And then I can construct a system of equations over these predicates. So if I have z equal f of y, then I know that the clocks of x, of z and y have to be equal at all cycles. If I'm writing y equals x when clock, then I know that the clocks of ck and x have to be equal. And the clock of y is equal to the clock of ck and ck. So it is true, y is present only when ck is present and true. And so on. And so to each line in a Lustre program, we associate these equations, and then we solve them using a low complexity calculus, which is often seen as part of the language semantics. So for instance, if I remove the when operation from here, I will require that G, which is a function, makes Z, X, and U have the same clock, but Z has the clock of Y, and Y is not the same as the clock of X. So this program is rejected as incorrect. The previous was correct. So this is how synchronous languages solve the problem of single assignment and causality. But this is not something that is unique just the solution is unique to synchronous languages. The same representation problem also exists when converting C to SSA. You need some form of undefinedness. You need in some cases to manipulate explicitly absence and reason about it. So for instance, if I write this piece of C code, then Y can be used in contexts where it is not initialized. And so to be able to translate this code fragment into SSA, and you know it very well, compilers introduce undefined values with names such as undef and poison, and which are part of the LLVM dialect in MLIR, which can be used in computations, and C compilers aim to preserve or refine these undefined behaviors. In the synchronous world and in Lustra, the approach is much more restrictive. Undefined values must never be used in computations or tests. So there is no need for complex undefined semantics at high level. You just reject it. And this brings us to a theorem that we proved, which is that given a correct synchronous specification where sync undef values are never used, sync undef can be lowered to any lower level SSA value. It can be LLVM undef or poison or a constant or an MLOC without initialization. And given this, we can define a lowering from loose to sync and then to standard dialects. The first one, the first step here is to perform the clock analysis on the code. So this code is correct, and absent values are never used. Then we, by taking the lines of the program in order, we will generate this sequence of code of basic this DAG of basic blocks, which implement the behavior in an imperative way. So here it's a move from data flow specification to imperative specification by making explicit tests that branch to executing F and G or not. And in this case, we initialize the output of G with undefined, and so on. And the Lustra absence here is lowered to sync.undef, plus some branching and merging at SSA level. Then from this, we can lower to standard dialects by replacing, for instance, sync.undef by LLVM.undef, but it could have been a constant. The second challenge, the internal state. So here is a stateful specification. It's a cyclic behavior that receives at each cycle one input and sums the values indefinitely, producing at each cycle the outputs. To represent it using our dialect, we have this loose dialect node, which mixes loose operations with TF, the data processing operations, and followed by here implements the memory initialized with 0, which is the value of C0. And then it elements the additioner, and at each cycle the output is the value inc is also provided at the output. Now, note that there's a mix of Lustre data flow control and TensorFlow data processing. It works seamlessly. And also note that there's a cycle here formed by the followed by and add operations going through S and inc, meaning that this node cannot respect the dominance property and has to be treated under MLIR relaxed dominance. But of course, this is good for entering the pipeline. But the first thing to do in order to benefit from SSA code transformations is a normalization phase, ensuring that dominance is respected. And this normalization phase will, first of all, ensure that all followed by operations are executed at each cycle. This may require some when and merge operations, multiplexing and multiplexing. And then group all followed by operations together and place them and model them as loop carried dependency. So recall that this is an implicit loop here. So we will place the output of followed by here. This is the state that can be used in computations, and the input of the followed bys is here in the yield operation. We disconnected the followed bys, placing one bit in the signature and the other in the yield operation. From this point on, inside the node, we have a direct, we have an acyclic graph of operations, and we can manipulate it inside MLIR without assuming a relaxed dominance. And the first thing we can do now is to transform this Lustre node normalize into sync reactive function. This is done by making explicit the infinite loop around this directed acyclic graph of operations, and then expanding the data flow control into explicit imperative control flow. This is the infinite loop here. And this is the body of the infinite loop. Cycles are separated by the tick operation. Then inputs and outputs become channels, read and written explicitly with input and output operations, and so on. And from this level on, to generate to complete the code generation, we only need to okay, one more remark here. The state of the node, the value of the followed by transmitted from one cycle to the next, is here a loop carried the dependency of the while, which is pretty good in terms of level of abstraction. And finally, by implementing all these high level, all these low level reactive primitives with API calls, we obtain the final implementation code, which can be transformed into binary code. And here you can see that the input channels become functions transmitted through reference to functions, and these functions are called, for instance, here, to get into a specific memory zone the value of the input that we want to acquire. Once this is done, the addition operation is performed, and then the output can be produced again through a call to an output function. This is a choice of encoding, but is done at the last stage of translation, not at the beginning. Okay, finally, modular execution. So we have now our integrator, which performs the sum of values at the input. We have compiled it it is a separate L file. And we want to call it from another node, which we call test. We do this using the last, at loose level, using the last that instance operation, which gets translated to the sync dialect level into the sync.inst operation, and then it is implemented through runtime API calls. One of which, yeah, I will not insist because I don't have more time left. At this point, I can show again the initial example, the recurrent neural network. So here you have the Keras code. It's a very simple network with 2 layers, an LSTM and a dense, which receives as the input 49 in Keras, 49 sequences of 49 time steps, each with a 40 a vector of size 40 sample. When translating it, we produce one node for the model, and one node for LSTM, one for dense, and one for the automaton that decides when outputs are produced. So we are trying to completely follow here the semantics of Keras, which only will output one prediction every 49 cycles, even if it's a reactive execution. And you can see here the implementation of, so here you have if you recall how LSTM works, you have 2 states. You have here followed by and followed by. You have a protocol that has to reset the execution every 49 samples, and the protocol is here, and is triggered. Oh, excuse me, and it's triggered by the arrival of the reset signal in the input of LSTM. Then all of these elements, the main data flow of the LSTM, the classical one, and then LSTM will produce its output. And this output is only fed into the dense layer that follows in the cycle before the reset. And this is, so dense is not executed at each cycle. And this is achieved using the when subsampling operator that will let x2 take the value of x1 only when ck is true. I will go quite fast. I already explained that our implementation is non-intrusive. We don't modify existing MLIR code. We only add a few code and reuse a lot. In performance, the result is that we don't pessimize code generation with our reactive encoding. And we tried 2 pipelines to check this, and a small pool of ML examples. In expressiveness, we can express quite complex reactive control and mixed with HPC data handling. And of course, we played with small ML applications. But in order to really push this more to the limits, we took non-ML application with complex reactive control, which is a pitch tuning vocoder, which is available on the download site I mentioned earlier, and you can try it. It's a soft real time. It will change your voice pitch from normal to either high or low, and it's running in real time. Current limitations of what we are doing. We don't yet do training. We cannot yet represent training in our framework. We can represent its results, but not the training process itself yet, due to backpropagation representation, which we still have to work on. It's our next paper, hopefully beginning of next year. We only describe activation, not task length. So which may be useful to represent resource allocation. Of course, what we do is already good for specification. So we already represent everything that Keras represents. But with a bit of extension, we should be able to represent also implementation side duration of operations, such as for high-risk scheduling, for multi-resource scheduling. Conclusions. Okay, what I hope to convince you is that MLIR needs a data flow dialect. It's natural because you have to deal with concurrent, stateful, predicated, and hierarchic specifications, and that really come under data flow form. It also allows, doing so would allow mixing the machine learning code with front end and back end data pre and post processing. And it's also natural for streaming and embedded, but it's not only, it's not something restricted to this. Why in MLIR? Because it would help streamline the specification and the compilation process and allow developing solutions common to multiple problems, that some of which have each one a separate solution, which do not combine well, some of which cannot be even specified today due to the lack of general purpose reactive specification. And of course, we propose that loose is a good minimalist, the data flow dialect, and we would like to work with you on perfecting it and maybe upstreaming it if everything is okay. Second, we proposed a number of low-level primitives for concurrent reactive systems. They are needed for reactive embedded multi-component implementation, not necessarily because the application itself is reactive, but also because the backends are sometimes a virtual machine like IRE is reactive, and it will interact with the front end in a reactive way anyways. We discovered that the primitives provided by existing dialects are not enough. And so we proposed extending this set with something that allows you to synchronize with the exterior, a high-level representation of cyclic I/O, and a way for components to give control to each other while maintaining an internal state. Another good property of this extension we propose is that it's easy to implement, has well-defined semantics, and it corresponds to what can be done with synchronous calls. More mechanisms may be needed in particular cases, such as asynchronous calls, and we have some ideas on how to do them, but we will need some examples. And I think I finished, and maybe you have questions. I'm sorry, it's a lot of matter I discussed about.
Thanks a lot, Dimitro. That was super well presented, so much that I didn't see the time flying by, and we're already at the end of the hour. Maybe we can take one quick question, but otherwise we're going to have to leave it for offline discussions on Discourse. Quick question, anyone? All right, I think we're going to pursue discussion on Discourse. So thanks again. It was very, very good presentation, and I think I have to rewatch it because it was also a lot of new contents for me, probably for Mani as well. So thanks a lot. Good end of year to everyone. See you next year.
Don't hesitate to send email and contact. And I will try to connect to Discourse, but I'm not sure how to do that.
Discourse, the forum, you've been posting there, didn't you?
Yes, but
Discourse.
Discourse, yes. I will try to do to connect now.
Sure. All right. See you there.